In honors pre-calculus, we learned that the area of a sector, or like a piece of pizza, is 1/2 r squared theta. Well, that's exactly what we use to find the area of polar graphs. We integrate from alpha to beta of 1/2 r squared, and then d theta is takes the place of theta. And we take an angle and we cut it up into infinite amount, or we make it infinitely smaller, but then add up an infinite amount of those. That's what integration is. So we want to find the area inside the cardioid, r equals 6 minus 6 sine. If we plug 0 in for sine, sine of 0 is 0, so we get 6 over here. Sine of pi over 2 is 1, so we get 0. Sine of pi is 0, so we get 6 over here. That'd be a radius of 6. And then sine of 3 pi over 2 is negative 1, so we get down here at 12. So here's the cardioid, something like that right there. Now we want to find the area of that entire shape. So we have 1/2 integral from 0 to 2 pi of r squared. So we want to square both sides there. So we need 6 minus 6 sine theta squared d theta. So there's the setup. Now the rest is really old stuff that we've been doing for quite a while now. We have 1/2 integral from 0 to 2 pi of 36 minus 12 sine of theta plus 36 sine squared theta. So just, it's FOIL. Excuse me. We know how to integrate all of this with the exception of sine squared. But if we look at the double angle formulas, if we start out with cosine of 2 theta, we can, what do? We replace this with 1 minus sine squared, which is 1 minus 2 sine squared. And then if we get sine squared by itself, we end up with that little equation right there. Now we can replace sine squared with 1/2 minus 1/2 cosine 2 theta. So let's do that. We have 1/2, 0 to 2 pi of 36 minus 12 sine theta plus 36 times 1/2 minus 1/2 cosine of 2 theta d theta. Let's distribute the 36. We have 0 to 2 pi of 36 minus 12 sine of theta plus 18 minus 18 cosine of 2 theta. Let's combine some like terms and then we'll actually integrate. So 36 and 18 is 54 minus 12 sine of theta minus 18 cosine of 2 theta. So we have 1/2 times 54 theta minus 12, actually plus 12 cosine of theta, and then minus 9 sine of 2 theta, and 0 to 2 pi. That's 1/2 times, when we plug 2 pi in for theta, we get 108 theta plus the cosine of 2 theta, or 2 pi is 1, so that's plus 12. But the sine of 4 pi is 0, so that piece goes to 0. Then minus, let's plug 0 in. 54 times 0 is 0. Cosine of 0 is 1. So we have 12, but sine of 0 is 0. So we end up only minusing 12 from this. Well, 12 minus 12 is 0, and 1/2 of 108 is, oh, that should be not a theta, but I plugged in 2 pi. That should be a pi. So half of 108 is 54 pi. Find the area inside the one petal of the rose, r equals 3 cosine of 2 theta. We got theta, we got r, we're going to plug in 0, and when we plug 0 in, 3 cosine of 0, well, cosine of 0 is 1, so we get 3. It's 1, 2, 3, so we're over here. Then we're going to double this, count by pi over 4. So we have pi over 4. Cosine of pi over 2 is 0. And so we're over to 0. So at pi over 4, we're at 0. Now that's half a pedal. So we can integrate 1/2 from 0 to pi over 4 of 9 cosine squared 2 theta d theta, but then double that. That'll be one whole pedal. The 2 and the 1/2 cancel out, and I can pull the 9 out here, but we still have kind of an issue here. We have cosine squared of 2 theta d theta. Back here, we have cosine squared is equal to 1/2 plus 1/2 cosine of 2 theta. But we don't have cosine squared theta, we have cosine squared of 2 theta. Well, the good news is if you replace this with 2 theta, cosine squared of 2 theta, you can just replace this theta with 2 theta. So cosine of now 4 theta when you put 2 theta in for that theta. So we need 1/2 plus 1/2 cosine of 4 theta. This is 9 times the integral from 0 to pi over 4 of 1/2 plus 1/2 cosine of 4 theta. And now we can do the integration. So we have 9 times 1/2 theta plus, let's see, I need a half when I multiply by 4. So what's that going to be? 1/8 sine of 4 theta? Yeah, because that'd be 4/8. When we take the derivative, that'd be 1/2. And 0 to pi over 4. So 9 times, let's see, pi over 8, right, when we plug pi over 4 in here. And then plus sine of pi is 0, so plus 0. And then minus, when we plug 0 in, we get 0. Plug 0 in here, sine of 0 is 0. So lots of zeros on this. So the answer ends up being 9 pi over 8. Now we want to find the area inside the 4 pedaled rows and outside the circle. Let's get an idea of what this looks like. If we plug 0 in for theta here, we get, well, the cosine of 0 is 1 times 4 is 4. 1, 2, 3, 4. So then if we plug in pi over 4 there, the cosine of pi over 2 is 0, and we get 0. So at pi over 4, we're back at 0. And here's an idea of what, let's see, 1, 2, 3, 4. Here's an idea of what this looks like. All these pedals, 1, 2, 3, 4, should be this, look exactly the same. 2, 3, 4, and something like that. Well, there's the 4 pedaled rows. We have a circle with a radius of 2. So there's a circle of radius 2. Now what we want is, it says inside the rows, outside the circle. So we want that area right there, except 8 of these. 2, 3, 4, 5, 6, 7, and 8 of those. So now we can write 8 times 1/2 integral from 0 to pi over 4 of 16 cosine squared of 2 theta minus 4 d theta. So we have 4 times integral from 0 to pi over 4 of 16 times 1/2 minus 1/2 cosine of 4 theta minus 4 d theta. Let's distribute the 16 just because it's even. Pi over 4, let's see, we got 8 minus 8 cosine of 4 theta minus 4 d theta. Well, 8 minus 4 is 4, so 4 integral from 0 to pi over 4. 4 minus 8 cosine of 4 theta d theta. So 4 times 4 theta minus, let's see, we have, I need an 8. So 2 sine of 4 theta from 0 to pi over 4. So 4 times pi, when we plug pi over 4 in, we get pi. And then sine of pi is 0, so we get 0 there. Then 0 minus 0, so the answer ends up being 4 pi.